Hello everyone, today I will share the work on the liver disease classification task. This project focuses on predicting whether a patient will suffer from cirrhosis based on clinical and covariate data. The dataset, sourced from the Mayo Clinic, contains records of 424 patients with primary biliary cirrhosis. These records include clinical and biochemical features such as bilirubin levels, albumin, and platelet counts. The target variable, originally divided into 4 stages, was simplified into a binary classification, 1 for cirrhosis and 0 for no cirrhosis. This classification enables a clearer focus for machine learning models. Pre-processing was an essential step to ensure data readiness. Missing values in numerical features were replaced with zeros, while categorical variables such as assets and ADAMA were filled with their most common value. Numerical features with high skewness were log transformed using np.log1p to normalize their distributions, making them more suitable for modeling. Outliers were identified using Turkey's rule and handled through winsorization, capping extreme values to prevent them from disproportionately influencing the result. Class imbalance was another key challenge, as the dataset had more records without cirrhosis than with it. To address this, SMOTE, a synthetic oversampling technique, was applied to the training set. This balanced the dataset, ensuring that the models had enough data to learn from both classes effectively. After pre-processing, the dataset was scaled using standard scaler to ensure all numerical features had a similar range. The first model applied to the dataset was a decision tree classifier. Decision trees are interpretable models, making them valuable in healthcare where understanding feature importance is critical. The decision tree classifier was trained on a balanced and scaled dataset and achieved an accuracy of 64.3% on the test site. The confusion matrix revealed that the model performed reasonably well in distinguishing between the two classes, correctly identifying 36 patients without cirrhosis and 18 with cirrhosis. However, it also misclassified 17 patients without cirrhosis and 13 with cirrhosis. This result reflected that the dataset's complexity and suggested the potential need for more robust models to improve performance. To explore alternatives, the dataset was analyzed using PyCaret, a low-code machine learning framework. PyCaret automated the comparison of multiple classifiers, including logistic regression and extra trees classifier. Among the tested models, the extra trees classifier emerged as the best performer, achieving a mean accuracy of 75.8% across cross-validation folds. This model outperformed the decision tree by effectively capturing complex interactions among features, leveraging its ensemble nature to reduce variance and improve overall stability. Validation was integral to this process. The dataset was split into training and testing subsets with an 80-20 split. 5-fold cross-validation was applied to ensure the models generalized well to unseen data. Metrics such as precision, recall, and F1 score were also used alongside accuracy to provide a more comprehensive evaluation. For example, the extra trees classifier achieved a recall of 60%, indicating its ability to correctly identify a significant proportion of cirrhosis cases. One of the critical theoretical considerations in this analysis was the bias-variance trade-off. The decision tree classifier as a simple model had lower variance but higher bias, leading to moderate accuracy and limited generalizability. In contrast, ensemble models like extra trees classifier reduced bias by combining multiple decision trees while managing variance through averaging. Hyperparameter tuning further optimized this trade-off, balancing model complexity and predictive power. The findings from the datasets highlighted several important insights. First, pre-processing steps such as log transformations, SMOT, and feature scaling played a pivotal role in enhancing model performance. Second, while the decision tree classifier provided interpretability, the extra trees classifier demonstrated superior predictive power, showcasing the advantages of ensemble models in handling complex datasets. Additionally, the feature importance analysis revealed the bilirubin, albumin, and prothrombin levels were critical predictors, aligning with clinical knowledge about liver function. From a real-world perspective, this result underscored the potential of machine learning to assist in healthcare diagnostics. Interpretable models like decision trees can help identify key risk factors, while more advanced models like extra trees classifier can provide higher accuracy for clinical decision-making. However, challenges such as class imbalance and noisy data must be carefully addressed to ensure reliable predictions. In conclusion, the liver disease classification project demonstrated the importance of combining rigorous pre-processing, thoughtful model selection, and robust validation techniques. By addressing key challenges in the dataset and leveraging advanced algorithms, this analysis provided valuable insights into the potential applications of machine learning in healthcare. Thank you for watching.